Okay, so we can continue. Welcome back. As I mentioned before, we will stay with the topic of humidity and moisture measurement. We will also stay with dew point and frost point calibration. But as I mentioned, I guess you have some different aspects and new aspects to tell us. So I'm happy to introduce our next speaker, which is Dr. Alexander Theis from DILO Armaturen und Anlagen. So it's your stage. Have fun. Stay tuned.
Yes, thank you very much. Also from my side, a warm welcome. And in my presentation, I would like to introduce our new adaptive dew point mirror that is actually based on a chilled mirror hygrometer, but which is optimized for industrial applications and calibrations. So who are we? Actually, DILO has a long-standing experience in gas measurement technology with more than 40 years of experience in insulating gases. And especially in SF6 applications, humidity plays a crucial role in, for example, assessing the gas quality and a reliable operation of the process. So our new adaptive dew point mirror concept would like to take this experience one step further, and we would like to use this experience to apply this to different other process gases as well as at the reference level. You see here, and this development, I mean, I'm just a presenter. This development is driven by our humidity team that you see here, and most of the people are around here, and you are very welcome to visit our booth. That is 1-324. So before we go into detail, and before I start to tell you something about the instrument, I mean, we have heard a little bit about, not a little bit, much about humidity in the previous two presentations. But here, first, I would like to show you what is actually humidity. So humidity is actually just the water molecules in a gas, and this can be a pure gas or a gas mixture. And humidity can be expressed by various humidity quantities. And here shown are just an example of some important humidity quantities, such as, for example, the mole fraction of water, and it is defined by the ratio of the number of moles of water molecules to the total number of molecules in that gas, for example, in a specific volume, as you can see here. Then another important quantity is the water vapor partial pressure. And the water vapor partial pressure is actually just the pressure, the contribution of the water molecules to the total pressure. For that, you have to know that all the constituents contribute to the total pressure, and the water vapor partial pressure is just the pressure the water molecules exert on the total pressure. Then we have another important quantity, that is the saturation vapor pressure, and the saturation vapor pressure can be understood as an upper limit. And when the water vapor pressure, for example, reaches the saturation vapor pressure, condensation sets typically in. And now, importantly, we have heard a lot about dew point or frost point, and but we haven't heard any definition about that, and here it is. The definition of the dew point, frost point is that temperature where the water vapor partial pressure equals the saturation vapor pressure. So this is exactly that temperature where the water vapor starts to condense. And if the condensation is liquid, we are talking about the dew point. And if the condensation is solid, then we are talking about the frost point. Also here, why it is important, especially for industry purposes. We have also heard a lot of this in the previous two presentations. I don't want to go into detail here, but from this table illustrates that there are a lot of industries that rely actually on a good humidity measurement, but for different reasons. For example, here we have for product quality, for chemical stability, let's say. We have here for safety risk, for corrosion, or also in general for the gas quality or the lifetime of the components, for example. Those are good reasons for an accurate humidity measurement, and especially when it comes to very low humidity values and humidity in different carrier gases, for example. So yeah, for most of you it might be a repetition from the previous presentation, but I would like to introduce it anyways, because maybe we have some new people here in the audience. So how does a chilled mirror or a dew point mirror work? We have here a cooler. We have here a mirror, which has a very flat, clean, reflective surface. And in that mirror, we have a temperature sensor, and then we have a LED, which illuminates here the surface. The surface reflects, and the reflection value is detected by a photodiode, a light detector in general. And now you can imagine if you have a flow from the left to the right, for example, of humid gas, and the mirror starts to cool, and it cools until a point where condensation sets in. And then the reflection value is reduced, and the control unit here says, okay, stop cooling and regulate to a point where the frost or the dew point is not changing anymore, at least not changing anymore significantly. So this is how it works. So it measures the dew or frost point, but for different applications, also in industry, some other humidity quantities might be of interest. So for example, the relative humidity, the mass and mole fractions, absolute humidity, specific humidity. So from that frost point, you calculate basically other humidity quantities. And some important parameters that influence the dew point or frost point measurement are the pressure, the flow, the gas type, and the phase of water on the mirror. And in the next couple of slides, I will a little bit go deeper into the parameters that influence the dew and frost point measurement. So yeah, here is our new adaptive dew point mirror hygrometer that is called Tau from the Taupunkt hygrometer. In German it is Taupunkt, and here we related this to the Greek letter Tau. And what it is actually a classical reference dew point mirror hygrometer, but it is optimized for industrial applications and calibrations. So what does that mean? It means actually you can, or it facilitates the measurement or the calibration on site. So it has a battery operation, and it comes in a portable trolley that is to a certain degree water protected and dust protected. So you can also use it in robust environments, let's say. And now the point is, why is it adaptive? And the reason, the clue here is that it has an automatic gas type detection. And this is what it makes adaptive. And I will explain it in more detail on the next slide. So how does it automatic gas detection work? So we have here a quartz tuning 4 oscillator. It oscillates in a specific frequency, and the equation is here on the right-hand side. And this depends on the density of the gas. And by calibrating the frequency to the with gases of different densities, you can relate by measuring the frequency. You can relate that to a gas density, and then using the ideal gas law, or you can also use real gas connected equations. For example, if just here the ideal gas equation, and by measuring simultaneously the temperature and the pressure, you get a molar mass. And then you can compare the molar mass to a specific gases, and this gives you a likelihood about the gas type you detect. And currently, we can measure hydrogen, for example, helium, nitrogen, oxygen, argon, air, CO2, and SF6. But more is, in principle, also possible in the future. So, yeah, we have here our automatic gas detection, and then we have a lot of advantages from that automatic gas detection, which are particularly important for applications in industry. So if, for example, for stable dew point measurement, you need actually also a stable flow and a correct flow. You have always a range where your chilled mirror hygrometer or dew point hygrometer operates in a good way. And in a classical chilled mirror hygrometer, they are usually optimized for nitrogen or air. And for example, if you have a measurement in CO2 instead of nitrogen, then your flow sensor will show the value that is correct for nitrogen, but not for CO2. So what you would need to do in that case, you have to adapt the flow manually. But if you have an automatic gas detection, you can, in the background, you know all the densities and the heat conductivity and the specific heat capacity and so on. And you can tell the flow sensor, hey, it is, for example, now CO2. Please use the correct parameters, and then the flow meter or the flow sensor displays the correct flow rate, volume flow rate. Yeah, so automatic gas detection enables gas-corrected flow indication and supports optimal flow settings. What you can also do is different gases might have, have different properties, for example, density, heat, mass transfer, thermal responses, and so on. And this might affect also the control loop of your dew point hygrometer. For example, if your instrument is optimized in nitrogen, and nitrogen, for example, is a very straightforward carrier gas, and if you have, for example, an optimized instrument for nitrogen, but you then measure in CO2, which has different properties, gas phase properties, so the stabilization, so what you see here, is a normalized optical signal. That means it is a reflection value divided by the reflection value of the clean mirror without condensation on it. And what you can achieve, then you can for each gas, you can optimize this control feedback, and the positive effect is that you have a faster stabilization time in that case. So automatic gas detection supports dynamic loop optimization. What you can also do is, with the automatic gas detection, you can display the correct values. For example, if you measure in different gases and at increased pressures, for example, your water vapor pressure behaves not ideal anymore. So you have to correct it with a real gas correction factor, and we call this the enhancement factor. And by knowing the gas type, you can also implement those enhancement factors, and then on the display of your instrument directly show, hey, the best value you can get, let's say. Shown here is enhancement factor as a function of the total pressure, and here for different temperatures and different gases. For example, blue is air, then orange is CO2, green is SF6, and the solid lines represent 20 degree plus, the dashed lines represent 20 degree minus, a frost point. And here, let's take an example of at 4 bars. So if we measure, for example, in SF6, so we would have a reduction in the mole fraction, for example, by 15% at minus 20 degrees C. And if we have this, if we compare it with at minus 20 degrees C for CO2, for example, this would still make an error of, yeah, let's say 6, 7, 8% or so. So it's quite important that you also can include this, and the automatic gas detection enables us to include those specific enhancement factors. Another important thing is in a classical chilled mirror hygrometer that is optimized, let's say, for nitrogen or air, when it shows, for example, other parameters like the mass mixing ratio or specific humidity, then those quantities depend on the molar mass of the gas. So here are the equations. We have here mass mixing or mixing ratio, for example. We have here the molar mass of water, but also the molar mass of gas. And by also measuring the gas type, we know the molar mass of the gas and can always display on the device the correct quantities such as the mass mixing ratio and the specific humidity. So automatic gas type detection enables automatic display of correct humidity quantities such as mass mixing ratio and specific humidity. And apart from the automatic gas detection, there are also some other important things to consider when you want to do a measurement with a chilled mirror hygrometer. And that is, for example, it is important to know on your mirror if it is liquid or it is ice. Because then you just, if you know the phase on your mirror, you know if you should use frost point or dew point, for example. And here we have a nice video. I hope it works out. And it doesn't work out. Can I go back to the... das Video anschauen? Okay, thank you very much. So what you see here is a measurement at minus 25 degrees C, and at minus 25 degrees C, you would expect, okay, hey, on my mirror, that's ice, but it's not the case. As you can see here, a lot of liquid droplets are forming, and if you would then say, okay, I have to take the frost point, you are wrong. This is here clear evidence. So you have a lot of droplets, minus 25 degrees C, and then on some nucleation sites, ice crystals are forming. And in this stage, for example, neither the frost or dew point is correct. So you have to make sure that you know the phase on your mirror. And it can make a difference of, let's say, 10%, for example. What you see here is the saturation vapor pressure as a function of temperature. And below 0 degrees C, the curves of the saturation vapor pressure for liquid water and ice water deviate. And this means if you sync your mirror, it measures at minus 20, but it should measure ice. But in reality, it's rather the dew point that is correct at that point. You make a difference, you make an error of, let's say, in this case, 2.25 degrees Celsius. And no matter how good your instrument accuracy is, the error is quite huge. So what we then do is, once we are below 0 degrees C, we cool the mirror to minus 40 degrees C, and then at minus 38 degrees C, this is a homogeneous freezing temperature, for example, and then we can make sure, okay, everything is ice on the mirror, and we have the correct value, and we know we measure the frost point then. If you won't have it, then you would have a very slow adaptation to the correct frost point value. Another important thing is that, for example, if you measure at very, very low humidities, for example, we are talking about then some hundreds of water molecules in 1 million gas molecules, and it would really take a very long time until you have a very stable value. But in this case, we don't want to wait so long. So what we do is basically we inject an impulse of high concentration of water vapor, and this increases basically the ice formation, and then we have the ice layer on the mirror, and then it stabilizes around that value. All right, so finally, I would like to also show some data of the instrument. So the measurement setup is as follows. We have here a humidity generator, and we have here our reference and our measurement device. And then we compare, we make a calibration by comparison. We heard a lot about it. So, and this is what it looks like. This is what we did. We've done a step test from low temperatures, frost points to high frost points, and from high frost points to low frost points again, and repeated this several times. And here on the first glance you see, okay, all instruments are very close to each other. You can hardly see a difference here. But then when we look a little bit in more detail, what we have done is at the stable area on the plateau, we make or subtracted both frost point values of our tau and the MBW, for example. And here the dashed lines indicate the 0.1 temperature range. And as you can see here, all the values are more or less well within that 0.1 temperature interval. We have here, one at the edge, but it has also a larger error bar. Okay, and when we take the reproducibility, and the reproducibility is determined basically by the maximum difference between the lowest and the highest point, and we divided it by a factor of 2. And this is the result here, for example. So all values are well below 0.05 degrees Celsius, except the one at minus 40. But I think if you would remove this, your result would definitely be inside that interval. But we are very close to that. So now I come to my summary and the conclusions. So our adaptive mirror concept builds upon reference standard dew point hygrometry and extends it for industrial gas applications. Industrial gas applications require gas-specific operation and evaluation, and automatic gas detection enables improved flow control, humidity calculation, control behavior, and possibly also gas-specific uncertainty estimations on the device itself. Our additional phase control features improve the reliability and the usability at low frost points. And the concept supports practical and traceable humidity calibration and application in different industrial gases. And now I'm at the end of my presentation, and I would like to thank you very much for your attention. And we would be happy to visit you at our booth for further discussion. And I'm happy to take questions. Thank you.
Well, thank you, Dr. Theis. And so we have some short time left for some immediate questions. People are very shy this morning. We have nearly no questions. So maybe most is said and done, but I think we learned a lot during the last 2 hours. We learned a lot about, at least I learned a lot about humidity measurement and frost point and dew point. Most of the stuff was pretty new for me. I think there are some or more experts in the audience. And okay, so thank you for now. And if you want to meet Dr. Theis at the booth number is on the screen, 324. And thank you again.